All right. Energy obviously is a really critical part of this course. And so what I want to do today in our first lecture, then we're going to have a break again, and we'll have another lecture. In our first lecture, I want to look at how energy is stored in a substance. Okay? There are different ways energy is stored in a substance. The two main categories are internal energy and mechanical energy. Okay? Are the ways energy is stored inside some kind of substance. And when I say substance, I generally mean a gas, a liquid, or a solid. Okay? And so the first one that we're going to talk about is internal energy. We're going to use the designation U for internal energy for the entire course. Okay? U means internal energy. And of course, the internal energy can be expressed in either joules or BTU. Okay, as we just discussed. Now, the other thing that I'm going to do frequently in this class is I'm often going to describe stuff as, instead of it being just an amount of energy, like joules or BTU, oftentimes I'm going to describe them as an amount of energy per mass. Okay, for instance, joules per kilogram or BTUs per pound mass, right? When I do that, I use lowercase, okay? So I use a lowercase u like that to mean joules per kilogram or BTU per pound mass. That's a lowercase u. Okay. That uppercase, lowercase designation should hopefully hold, I hopefully don't screw that up, hopefully hold every time in the class. If it's lowercase, it's expressing that amount as per kilogram or per pound mass. Okay? Now, what is internal energy? I think the way that I visualize internal energy is to think of some kind of liquid and think, okay, well, what's inside the liquid? Well, a bunch of molecules. All right? A bunch of molecules inside the liquid. And each one of those molecules is moving around. Okay? In a liquid, they don't just sit there, they move around. Okay? They're easily mobile. Okay? The faster they move around, the more energy is stored in the molecular motion. Okay? Now, that's not how you see internal energy, but that's what's going on if you were to look inside at the molecular level. The molecules are moving around. The faster they're moving around, the more internal energy is going on inside. Okay? The way typically you see internal energy is actually quite simple. If something's hot, you go, oh, that's hot. That has more internal energy than something that's cold. Okay? You don't see the molecules moving faster. You just go, oh, that's hot. Okay? That's hot. And hotter stuff has more internal energy than colder stuff. Okay? All right? So when we really see it as it's the energy stored as, it's not really stored as heat. That's not really proper thermodynamics. It's really energy stored in molecular velocity, but it's practically speaking, it's energy stored as heat. Okay, as a higher temperature. Okay, so it's proportional to temperature. There is no such thing as an amount of heat inside something. Heat is only in transfer. But people say that all the time. So it's enough to, help you understand. The amount of internal energy is proportional to temperature. Okay? It's also a property, which means that you can look it up in the back of the book. It's in tables. Okay? And not that you need to do this right now, but if you were to do this and go to the back of your book and you were to look up some of the different tables back there, you don't have to do this, but if you were to do that and go to the back of the book, you can find all sorts of tables that have a little U in them. And the U is for internal energy, okay? And we're going to use that quite a bit. Okay? The U is for internal energy. It's the amount of energy stored inside the substance, in the liquid, the gas, even solids can have internal energy. Okay? And again, the hotter something is, it has more internal energy. That makes sense to us. Right? It makes sense. Hotter stuff has more internal energy than colder stuff. If something's really hot, like boiling water, you turn off the stove, you leave it, you come back in the morning, it's colder, right? It's probably room temperature. That energy that was inside the water has transferred to the room. Okay? It's transferred to the room, your kitchen, whatever. Right? So that's energy that has left the internal energy of the water and transferred into the internal energy of the air surroundings. Okay? You would heat up your kitchen, your house, whatever. You know, not a lot, but a little bit. That's internal energy. That's stored energy. Okay, now, mechanical energy. Mechanical energy has three parts, two of which I think you know about. And I think in fact, we've already been talking about it, right? First one is potential energy, okay? Probably done this in physics, not that hard, right? Potential energy basically says this. Stuff that's higher has more energy than stuff that's lower, okay? And you might have a datum here, and a datum is just an arbitrary line that we create, and then we say, oh, okay, well, this box is at a height h, and that box at a height h has more energy than the box on the floor, because I could take that box at height h and let it go. It could fall, and if I had a pulley system, the falling of that box could lift something else, right? Or I could spin a wheel with it or something, right? I can use that energy of potential energy, and I could convert it into mechanical energy, right? You know, you can do a lot of stuff with it. Okay. In fact, hydroelectric power is pretty much all comes from potential energy, right? We have water that's higher than some other place. We have waterfalls, things like that, and we go, that water is falling, it's losing energy. Why don't I capture some of that energy, make it spin something, and when it spins something, it's basically spinning a generator that's generating power, right? So that's turning potential energy into electrical energy, okay? So obviously potential energy is very important. It is an important factor in certain applications. And I hope you know, that potential energy is equal to mgh. That's the most common formula. Mass times gravity times the height. Okay? But in this class, what I like to do is I like to express things on a per mass basis a lot. Okay? On a per mass basis, I'm going to do this. Potential energy per mass is simply just G times H, right? Just knock off the M, divide out the M. Sometimes we'll express that, instead of G times H, you'll see a lot of formulas in the book and other places do G times Z. Z is the same thing as H. It's basically the height. Okay? But I'm just telling you. Okay? The units on this are joules per kilogram. Same units we're used to. If it's per mass, the units of energy per mass are going to be joules per kilogram. Now, of course, the units of potential energy, if you do mgh up there, those units are joules. But if you do it per mass, it's going to be joules per kilogram. Okay, I'm hoping that most of you have seen potential energy, and it's not a big deal. Okay, and it also comes up in your dynamics course. It comes up in physics, things like that. Basically says energy is higher. If something is higher, there's more energy than something that's lower. That makes sense. Okay, but let me finish with this one point. In most cases, potential energy is small. Okay? In most cases, not all cases. Sometimes potential energy is very significant. But I will tell you that in most cases in this class, potential energy will be small. We will not use potential energy very often. Okay? We will use it some, though. obviously, or I wouldn't introduce it. This may beg the question, how do you know in a given problem, in a given situation, whether potential energy is negligible? Negligible is just a fancy word for small, zero, nada, ignore it, whatever, right? Is it negligible, small, whatever, or is it significant and I need to include it in my analysis? How would you know? I will give you a clue. The reason you would know is because the problem gave you some kind of height. It said the water flowed from 80 meters above down to something like that. It gives you some kind of height. That's probably a clue you need to use potential energy. Okay? If there's no information given about the heights of anything, elevations, anything like that, if you have no knowledge of that, potential energy is probably not significant. Okay? And I'm going to work a problem later on and show you that there are many cases where potential energy is tiny when compared to other forms. Okay? But sometimes it's significant. Sometimes it's very significant. Okay? It's not always like this, but in many cases it's small. All right. Kinetic energy. Well, we just talked about that. I just said kinetic energy is equal to 1/2 mv squared, right? Okay? And so the units would be joules. But I can also express kinetic energy on a per mass basis, which is done often in our formulas, as 1/2 v squared. So those units would be joules per kilogram. And of course, when I say those units, this could be BTU, and this could be BTU per pound mass. Okay? This second equation, just 1/2 v squared, does throw off some students sometimes because they're not used to kinetic energy just being 1/2 v squared. It looks a little odd to say kinetic energy is just 1/2 v squared. Yeah, if it's per mass. If you divide out the mass, it is. Yes. Okay. Now, let me give you a quick example too of the units. What's typical units of velocity? Meters per second. That's most common we're going to see. Let's say we got velocity in meters per second. If I plug it into that kinetic energy formula, what are my units going to be? What's 1/2 v squared, the second one? If I plug that in there, what are my units going to be? Just the units. Meters squared per second squared, all right? I'm claiming meters squared per second squared has the same units as joules per kilogram. So I thought it might be a good idea for me to show that to you. Because you might go, I don't see how meters squared per second squared equals joules per kilogram. I mean, it's not obvious. You know, right? Okay, a joule, as mentioned before, a joule is equal to a Newton meter. So this is equivalent to a Newton meter per kilogram. Okay? Okay? So we're getting somewhere. Now the question is, what's a Newton? What's a Newton? Newton is a force. It's a force, but what's its units if you break it up? A kilogram meter per second squared. A Newton is a kilogram meter per second squared. So I'm going to take that Newton and replace it with a kilogram meter per second squared. Now multiply by a meter, divide by a kilogram. Now you can clearly see that the kilograms on top cancel with the kilograms on the bottom, and the product of the top is clearly meters squared. Right? So basically I made the claim and then I stepped this over to prove that claim. Okay. Again, I hope kinetic energy is something that you've seen before. You're certainly going to see it in dynamics. We are going to deal with it in not in static, but in thermodynamics some. In physics, I hope you've seen it before. It's pretty basic, right? Again, in most cases, not all, in most cases, kinetic energy is small. Relative to the other energies that we have. Not always, because obviously if it was always small, we wouldn't touch it. Okay? We'd probably ignore it. But in most cases, kinetic energy is small. It's not significant. When in a problem that you get and you read the problem, you might ask yourself, how do I know whether to make kinetic energy small or not? Any clue? What did I tell you for potential energy? What did I say for potential energy? How would you know it was small? If they didn't give you any height information, what would they not give you in a problem to make you think that kinetic energy was small? Velocity information, yeah. So let's say you have no idea of the velocity of the airflow or the velocity of the water coming down somewhere or whatever it is. You don't have any velocities. If you have no velocities given, they must be small, okay? But sometimes velocities are very significant. In fact, if you deal with nozzles and diffusers, if you're dealing with propulsion devices, things like that, if you're dealing in aerospace type of applications, okay, the kinetic energy is very significant, okay? If you've got some kind of nozzle that has an output of 500 meters per second, it's probably significant, okay? All right? But in most cases, it's not very big, okay? So we'll have to, as you go on, hopefully you'll see and go, oh, yeah, this is clear. I don't know any velocities, so therefore it must not be that critical, okay? Okay, let's go on. And this third term, I was hesitant a little bit to talk about the third term because, one, you've never heard of it. Two, we're not going to deal with this term directly for a while, okay? Because this term applies to control volumes. And remember what I said last week about control volumes. Control volumes is when you have flow in and out of a system, okay? Now, most things do behave as control volumes because most things have air, water, fuel, whatever going in, and have air, water, fuel, exhaust, whatever coming out, right? Things have flow, okay? But what we're going to do for the first month or so is focus on the closed system, okay? So there's no flow. So this is not going to apply for closed systems. Okay? This is only for open systems, for control volumes later on. But since we're putting together all the energies, I thought we better put together this one, okay? Basically, again, just underline control volumes. It occurs when the fluid is flowing. It's only applicable in control volumes, okay? What it accounts for is that when you have flow at high pressure, that has more energy than the same flow at lower pressure, okay? Flow at high pressure has more energy than flow at low pressure. That's all, okay? So it basically accounts for the fact that fluid flow at high pressures have more energy. Okay? Now, I don't expect you to go, oh my gosh, I totally understand, this is so clear. Oh yeah, of course, this makes total perfect sense right now. That's okay. No. Okay? It accounts for the fact that fluid flow at high pressures, it's not the clearest pressures, let me try to make that clear, have more energy. So the flow energy is equal to the pressure divided by the density, or more commonly we'll use pressure times specific volume. Okay. In the units here, I notice I wrote a small e. Small e means this must be per mass, joules per kilogram, or BTU per pound mass. Okay? Yeah? For incompressible fluids, like, yeah, you can still have that for incompressible fluids, yes. Yep. Yep. Because you can still pump them up to higher pressure. Okay. All right, now the reason I bring up all these terms, don't get too hung up on the flow energy term just yet, because we'll get to it later, okay? The reason I bring up all these terms is to say, what's the total energy in a closed system or controlled volume? Remember, a closed system does not have flow energy. So the total energy E can be expressed as the summation of the internal energy plus the kinetic energy plus the gravitational potential energy. And again, those units could be joules per kilogram or BTU per pound mass. Okay? Notice I wrote everything as lowercase u, lowercase e. That's all per mass. Okay? Now, in a control volume, you have the extra term, the flow term. So the energy term looks almost the same. U plus PV plus V squared over 2 plus GZ. Okay? And again, very similar. Okay? Okay? All right. One more thing here. Mass flow. Mass flow rate is an important property. And we deal with it often, especially in control volumes, obviously, because it's a flow. Mass flow rate is usually emphasized by m dot. Just as a side note, when I put a dot over the top, the dot means per unit of time, but it's really per second. Because I don't think we'll ever do much else besides per second. So every time you see a dot over top of a letter, that means it's basically per second. So m dot means mass per second. Obviously that's flow. Mass per second. Okay? Now the mass flow rate, by the way, can also be expressed as equal to the volume flow rate times the density. This may be helpful for your homework for those of you who have not finished it. The mass flow rate is equal to the volume flow rate, V dot, times the density. And again, V dot is the volume flow rate. Okay? This gives us one more way to express the energy balance. Take a look at that energy equation I wrote for control volumes. Notice this. If you have a mass flow rate, that's going to be something like, for example, kilograms per second, right? And let's say I have an energy term that's something like joules per kilogram. It's pretty clear when I do m dot E, right, if I multiply those two things together, something kilograms per second multiplied by something joules per kilogram, I get joules per second, right? Which is the same thing as a watt. So if you take the mass flow rate and you multiply it by the energy, you get a power. You get power. Okay? So if I want to figure out the power, which I would represent as E dot, because it would be like energy per unit time, that'd be power. That'd be the mass flow rate times little e, okay, which is equal to the mass flow rate times U plus PV plus V squared over 2 plus GZ. Okay, and the units would be joules per second or watts. That's simply just multiplying those two together. We're going to do that a lot. Mass flow rate we use all the time. Okay, one more thing. We do this a lot too. Remember last time I talked about the states? We're going to talk a lot about state 1, state 2, state 3, state 4. We're going to take a substance and turn it from state 1 to state 2. And a substance from state 2 to state 3, and state 3 to state 4, whatever. Okay? So oftentimes we look at a process which takes something from one state to another state. Okay? And we want to figure out what's the change in energy of that process. Well, you can write something like this. The change, at least in terms of power, is equal to m dot E, sorry, oops, m dot, it's not delta E, which is going to be m dot, and instead of looking at, we'll have to look at the change. So it would be like U2 minus U1 plus P2 minus P1V plus V2 squared minus V1 squared over 2 plus G times Z2 minus Z1. That's the last formula. That's basically saying the change in power between 2 points can be expressed that way. It doesn't always have to be multiplied by m dot. That's just an extra thing. It doesn't have to be. It could just be the change in energy. We'll do both equations, with and without m dot. But if you want to know which one has a higher total energy, you have to compare the internal energy of 2 to 1, the potential energy of 2 to 1, the kinetic energy of 2 to 1, and the flow energy. You have to compare all states. And then you can figure out the change in energy between the two states. Okay? This will become more clear as we go on, as we do more examples. Right now, we're just trying to get the basics down.